Intercepts are 2, 3, and 2. So how you're going to do this is 1 by 2, 1 by 3, and 1 by 2, isn't it? So what is the LCM of this? It is 6. So you have to just multiply 6 with all of them. So this will be 3, 2, 3, isn't it? Are you following this? Yes, no, don't know.
Yes, sir.
Yes, sir.
Okay, good. 3, 2, 3. Okay. Let's say you have a plane like this. So this is neither intersecting the y-axis nor intersecting the z-axis. So that means y and z coordinates. That means k, l, n will be 0. And it is intersecting the x-axis at some point which we don't know. But we are putting this 1. Can you tell me why are we taking this 1? Because we don't know whether this distance is 1 or not. It can be 2 also. On what basis we are taking it as 1?
Because
Let's
it's a
say,
unit cell something.
yes. So let's say it is some arbitrary distance a. So this will be 1 by a, 1 by infinity, and 1 by infinity. When see we take the LCM, right? So in that sense, the Miller indices for this or whether it is this, it doesn't make a difference. All are parallel planes. So we just take the, I mean, what to say, the HCF kind of thing. Okay, so 200 and 100, they would mean the same category of planes, okay, which are parallel to each other. So in that sense, we are taking this as 1. Can you tell me the Miller indices for this? So I say minus 3b and 4c. These are the intercepts. What will be the Miller indices for this? Can you calculate and tell me?
6 minus 4 and 3.
It's 6 minus 4 and 3. Yes. It's the same way of calculating. Okay. Just this is minus, so a bar will come here. Okay. Fine. Going ahead. So these are the things you please remember. Okay. See, you can by the way which I have taught you, you can always calculate the Miller indices of all the things. But remember, I told you, right? The competition is not about being right or wrong, but it's about who does it faster. So at least for these planes, so the XY, the plane parallel to the XZ plane, the plane parallel to the XY plane, and so on. Please remember these things directly. Don't spend even 5 seconds of time in the entrance examinations spending on like to analyze what will be the Miller indices of these planes. This should be remembered by heart. Okay, there is nothing wrong about this. It's a competition. Okay. So what is this plane? This plane, it is you can see that it is cutting two of the axes, but one axis it is parallel. Okay, so it's 110, 101, and 011. And the planes which are cutting all the three axes, let's say the positive parts of all the three axes, it is 111. If it is negative of some of the axes, it is 1 bar 1 1, and so on. Okay, so the standard planes, please remember the Miller indices. Okay, you should not analyze these things in the examination. Okay, by your practice, you should remember these things. If it is any arbitrary plane, let's say on the x-axis it is cutting 2, y-axis is cutting 5, z-axis is cutting -7, then you please analyze. There's nothing wrong in this. But at least these planes, these three types of planes, you should remember for your examinations. Okay, next comes a very important part, which is called interplanar distance. Okay, so I mean, I'm not going to derive these things, but I'm just going to give you some formulas which comes very handy in solving questions. So for the net and gate point of view, remembering this formula is a good idea. Planes are identified in terms of Miller indices HKL, as we know. Once you have that information, you can use that formula to calculate the interplanar distances. That means if these are the axes, this is one plane, then this is another plane, then this is another plane. Okay. So these are different planes which are arranged in a parallel fashion. What is the distance between these two planes? That is called the interplanar spacing. Okay. In any solid state physics book, you can find the derivation for this when all the angles alpha, beta, and gamma are 90 degree. And that is given by this kind of formula. You remember orthorhombic, alpha, beta, gamma, everything is 90 degree. Okay. So D is the interplanar distance for this HKL plane. HKL refers to the Miller indices. It is given by D is equal to 1 by root over H square by A square plus K square by B square plus L square by C square, where HKL, what are these? These are the Miller indices, and A, B, C are the those lattice parameters. Okay, in the table, Bravais lattice table, we used to say, right, A not equal to B equal to C. These things I'm talking about, A, B, and C. So one caution I'd like to give here, somebody is unmuted, please mute yourself if you don't have anything to say. Thank you. See, one of the greatest confusion people have is, in all the solid state books, you will find that this is derived. Okay, this formula is derived. But this formula is only true when your alpha, beta, and gamma are 90-degree. Okay. Some books mention this, some books don't mention this. And people, whenever they see any question in interplanar spacing, they apply this formula directly without thinking. And you will end up getting negative marks. Okay. Because you are in a hurry, right? Whenever you are writing a 3 hours exam, you have to solve hundreds of questions. So you are always tempted to use the formula that you know. But this is true only when you have, because what is the basis of this? The basis of this was cos square alpha plus cos square beta plus cos square gamma is equal to 1. Okay. Okay, this is true. We used to do something like this in the derivation. Okay. So that is true only when all the angles are 90-degree. Wait, this alpha and beta are not those. If this is the lattice, these angles are 90-degree. Only in those kind of lattice you can use this formula. Okay. Let's say cubic. In cubic also, okay, one disclaimer, this alpha, beta, gamma are different from this. Okay. Okay, when you look at the derivation of this, you'll remember things. Please look at that. But something like this, I remember we used to do in the derivation. Okay, that is not applicable when you have things like hexagonal, when one of your angle is 120-degree. This formula is not valid. Okay. So as of now, considering the interplanar distance, remembering these four are generally enough. Remembering these four. Okay, questions are seen to come only from these four: cubic, orthorhombic, tetragonal, and hexagonal. Out of these three, cubic, orthorhombic, and tetragonal. Remember CTOM, CTO. These three has alpha, beta, gamma is equal to 90-degree. Then you remember beta goes off, then gamma goes off, and so on. So there you see that the formulas are same. It is 1 by d square is equal to h square by a square plus k square by b square plus L square by C square. In case of cubic, this has become A square. Why? Because cubic has A is equal to B equal to C. So we can replace all of them with A square. In case of tetragonal, you remember A is equal to B not equal to C. First cut. That's why it becomes something like this. So in case of these three, remembering this formula is enough. Okay. But for hexagonal, things are different. Hexagonal, you have to remember this formula. You don't need to worry about the derivation of this. But for interplanar spacing of hexagonal, which is frequently asked in the competitive exams, the formula for interplanar spacing is this. It is 4 by 3 h square plus hk plus k square by a square plus l square by c square. Are you able to follow this? This slide is very, very important. Interplanar distance, it is frequently asked even in your job entrance test. Okay, they will just give you Miller indices or maybe the lattice vectors, and then they will ask you to find the interplanar distance. And people are often tempted to use this formula always. This is not a universal formula. For hexagonal, this formula is not valid. We have a different formula. Please note down this formula. Okay, you'll have to do a question on this. Shall I go to the question? Yes, no?
Yes, sir.
Yeah.
Okay. Okay, so please try doing this question. Those who are lying in the bed or reclining in a sofa, I hope you have some pen and paper with you to do these questions. Try doing this question. It came recently, 2020 June. You are given the unit vectors of a lattice. Unit vectors of a lattice are given. The spacing between 100 planes. So a particular plane is given 100. 100 plane means what? That this plane. We have recently discussed this plane. So it is asking you what is the this distance. Given the lattice vectors are this. Please try doing this. And if you want to note down any formula, you can take a screenshot of this slide. Let me see who gets the answer first.
Yes.
Yes. Who is this?
Ilamadi.
Okay. What is the answer?
C. Yes.
B. Okay. Wait. What is your name? You said
Ilamadi.
Ilamati. Ilamati. Okay. I'm just checking the spelling from the participants. Ilamati says the option is C. Okay. First answer. Anybody else support Ilamati or oppose him, saying you are wrong, you are right? By the way, Ilamati, how did you get his option C? What is your approach?
Using tetragonal form.
Tetragonal. Okay, you are saying that the lattice is tetragonal. C Tom, C Tom. So C Tom means A is equal to B, not equal to C. So you are saying that this and this. Are you sure this is tetragonal? What about other people? Ilamati is saying that this is a tetragonal lattice where A and tetragonal is two of the sides are same, but the third is not the same. Did you calculate the angles? Because tetragonal also says alpha is equal to beta is equal to gamma is equal to 90 degree. Are you sure that all these three angles are 90 degree? Ilamati, from where are you?
Gandhigram.
I mean your college?
Gandhigram Rural Institute, Dindigul.
Okay, okay. So where is this institute? Is it in Tamil Nadu?
Yes, sir. Tamil Nadu, Dindigul.
Okay, okay, great. Okay, so what about others? Ilamati claims answer is yes. Somebody else?
I think this is hexagonal.
Who is this?
Sandeep, sir.
Oh, Sandeep. Sandeep says this is hexagonal. Okay.
I am guessing, I am not sure.
Okay. So I bless you so that by guessing one day you qualify all these exams. Okay. But when somebody asks you, don't tell I guessed. Okay. Else students will be guided in the wrong direction.
No,
Okay.
no, sir.
Hmm.
This is not hexagonal.
This is not hexagonal.
Hmm.
Okay. Then why did you make me right?
I am changing my opinion now.
Okay. You are
Answer
changing your
now.
opinion now. This kind of confusion will kill you in the CSI net. Okay.
Sir, this is
Yes.
hexagonal.
Somebody else. It is hexagonal. Who is this? Some lady voice?
Sir, co-pair Navy, sir.
Huh?
Co-pair Navy, sir.
Wait. Let me just see the names. Okay, just tell me. Okay, somebody is saying it is hexagonal. On what basis you are saying it is hexagonal?
Sir, I did a project on hexagonal, sir.
Oh, you did a project on. Okay, experience matters. Okay, hexagonal. Anybody else? Okay, fine. This is hexagonal or tetragonal, whatever it is. What is the answer? Can anybody get the answer to this? 35 attendees. Anybody with the answer? See, the first task is to decide it belongs to which category of lattice. Is it cubic, tetragonal, hexagonal, or whatever? Okay. Okay, let me just cut down this tetragonal. Tetragonal is not a possibility, Lamati. Do you know why? What is the magnitude of this? The magnitude of this is A. What is the magnitude of this? The magnitude of this is also A. But this apparently looks to be different from A, but it is not. Why? Because something I cap plus something J cap. So what is the magnitude? Root over minus A by 2 whole square plus A root 3 by 2 whole square. That is A square by 4 plus 3A square by 4 root over. That is equal to 4A square by 4. 4 cancel. That is also equal to A. So this is a condition where your A is equal to B is equal to C. So tetragonal is not a possibility. Hence answer C is not a possibility. Ilamati, are you following this?
Yes, sir.
Okay, tetragonal is not a possibility. But A is equal to B is equal to C need not be hexagonal. It can be cubic also. Okay, how do you decide whether what is it? Whether it is hexagonal or whatever? For that, you have to decide on the angles. Okay, you have to decide on the angles. Let us check angles. Okay, let me calculate somewhere here. The first angle, I'm calling this as, let's say alpha. Alpha will be the angle between this and this. This has I cap and J cap, and this has K cap. So if you do a dot product, I cap dot K cap is 0 and J cap dot K cap is also 0. So the dot product of A2 and A3 is 0. So that means when the dot product of two vectors are 0, what is the angle between them?
90 degrees.
90 degree. Alpha is 90 degree. What is beta? Beta is the angle between A3 and A1. This is I cap, this is K cap. I cap dot K cap is 0. So what is beta?
Same
Again
90
90
degrees.
degree, 90 degree. But what is the angle between, what is gamma? Gamma is the angle between A1 and A2. If you see here, there is I cap and I cap. I cap and J cap will be 0, but I cap and I cap is 1, right? So this will be cos of gamma is equal to A1 dot, it's not this, this will not A1 dot A2 divide by mod A1 mod of A2. Okay. A1 dot A2 is nothing but minus A square by 2. And mod of A1 is A, mod of A2 is A. Okay. Because we have just checked, all of them are value A. So A square and A square cancel, it is minus half. So cos of gamma is minus half. So what will be gamma? Minus half
120
means
degree.
cos of 180 minus 60 degree. Cos of 180 minus 60 degree is equal to cos of 120 degree. So gamma is your 120 degree. So this is nothing but your hexagonal. Are you able to see this? So first we have to decide that this is a hexagonal lattice. So in case of hexagonal lattice, what you have to do is the spacing 1 by d square is equal to, what was the formula? 4 by 3 h square plus hk plus k square divide by, what was that? Is it a square?
A square.
Plus, yes, plus it is L square by A square, isn't it? Is the
C
formula
square.
correct? Okay,
L
just
square
let
by
me.
C square.
L square by C square, okay? L square by C square. Now our plane is HKL is equal to 1, 0, 0. So we don't need to worry about these parts. K 0, L is 0. Only this part will be contributing. So 1 by d square will be equal to 4 by 3. H is equal to 1 and A is equal to A. So that means d square will be equal to 3A by 4. So D will be equal to root 3 A by 2. Are you getting? So the answer will be A, root 3 A by 2. Anybody didn't understand, please raise your hand or ask directly.
Sir, in hexagonal
Sir.
A not equal to
Yes,
C.
yes. Oh, somebody is saying, Sandeep, let him say.
Sir, in hexagonal A not equal to C.
In hexagonal A is not equal to C, yes. But still this formula will be applicable here by putting C is equal to A. Why I'm saying is because I told that these three formulas are equivalent. One is related to the other. The difference is only the length of the sides. Okay. So in while deriving this formula, what is more important is the angles more than the sides. Okay. You see the structure of all these three are same. Why? Because the angle between them is same. Similarly, even if this is not hexagonal, even if this is not hexagonal, you just need to put this is equal to A. And this is anyway not going to matter since L is equal to 0. Are you getting this? More important is the fact that gamma is equal to 90 degree and alpha is equal to beta is equal to, sorry, gamma is equal to 120 degree and alpha is equal to beta equal to 90 degree. Is this point clear? While deriving this, the angle between the vectors is more important. Okay. Side value you can just adjust here. Is this point clear?
Okay, sir.
Okay, Sandeep, you are asking something?
I was also the same doubt. So.
Okay, fine. So, okay, this thing you can remember that this formula, even if all the sides are same, but the angle is this 90, 90, 120, you can use this formula. Okay, for this hexagonal thing. Okay. So what did we do? Firstly, we calculate all the lattice constants A, B, and C, found that everything is equal to A. Then the angles alpha, beta, gamma is equal to whatever 90, 90, and 120. Then we have put the appropriate formula and we got the answer. Okay, this is the way we have to do this. Is this fine? Is this point fine? So even in this, let's say what you did first was, okay, so I'm just with experience, how will you reduce the time? With experience, how will you reduce the time of solving these questions? Again, just like yesterday. Let's say you have these three vectors. The first thing that you did was calculate the angle between them. Okay, A1, A2. So I felt like calculating the angle between them. I got A1 dot A2 is minus half. That minus half factor is coming. A1 dot A2 divided by mod A mod B is minus half. So that means what came is angle 120 came. So whenever 120 comes, I had an intuition that only hexagonal has this 120 business. Okay, so hexagonal has this 120 business. So that means hexagonal will definitely have this 3 by 4 because the formula have that h square plus k square plus hk divided by a square. Since 3 by 4 will come. From there, I can directly guess that what to say? Sorry, it's 4 by 3. 4 by 3. 1 by d is equal to 4 by 3. So something like d will be equal to root 3 by 2 will come. Are you getting? If 1 by d square, anyway, the plane is 1, 0, 0. So this h will be 1. Okay. So 1 by d square has something like 4 by 3. So 1 by d will have 2 by root 3. So d will have some factor like 3 by root 3 by 2. So from there also I can guess that this will be correct. Are you getting, Sandeep? If you really want to guess in the examination, guess like this. Okay, this is the
Yes,
way
sir.
to guess. It is going to save some of your time. Okay, but that will be true only when you see that this feature root 3 is not present anywhere else. Okay, so this will come with practice. Okay, initially you do the way I have taught from beginning all the steps, but later you just look features. Remember this word, features. Look for a particular very strong feature in the question and look for that feature in all the options. It is very, very likely that only one option will have that feature. In this case, it is root 3 by 2. This feature is only in one question because the examiner wants to check your smartness. Okay, that's why he will deliberately keep a easy way. He will deliberately keep an easy way so that, see, why I'm telling this, when he has to filter some 200 students out of 10,000 students. He have to keep some alternate easy ways so that based on the time factor, some smart guys will be able to catch these features and get to the options, while others will be doing it right, but they will be able to do less number of questions. Why? Because they are doing in the rigorous conventional ways. Okay. So what I'm stressing is, please, once you are done with a question, don't go to the next question. Please question yourself 3 to 4 times. Can this be done easily? Can this be done easily? Okay. Just like in this question I told, just by doing a dot product of this, you will get an intuition. This is hexagonal. Hexagonal, this means 4 by 3 will come. When you take a root, 2 by root 3 will come. 2 by root 3 is present only here. These kind of things, please see. This is the way to crack the exam. Okay. Fine. Try this. This is not that tough. Some of you should be able to do this. And no guesses, please.
C.
Option C. Who is this?
Mouse.
Who is this? Mosam. Okay. Okay. So for simple cubic, I'm just writing down the formulas.
Yes, sir. Option C is also mine.
Okay, good. Okay, so initially it was a simple cubic. So everything was A, isn't it? Everything was AC. Okay. So what will be the interplanar spacing? It will be AC divided by h square plus k square plus L square, isn't it? So this is equal to AC divided by 1 square plus 0 square plus 1 square, that is root 2. Okay. What about this? D is equal to 1 divided by, this is the formula for tetragonal spacing. Please look at the slides. Okay, you cannot look, but I hope you have the screenshot. This will be 1 divided by h is 1, k is 0. What about a? A square is this one, root 2 AC. So this will be 2 AC square plus L is also 1, and this is 2 AC. So it will in square will become 4 AC square. Okay, there is a square root over this. So this is going to become, if you take the LCM of 4AC square, so this is going to become 2AC divided by root 3. Are you getting this? In case of tetragonal, are you getting the value of D to be 2AC by root 3? Mosam, Sandeep?
Yes, sir. Yes.
Mosam?
Yes.
Okay. So all you need to do is now, what you have to do is take the ratio. Take the ratio. If let's say this is D cubic, this is D tetragonal. What the question is asking you, DC by
Yes.
TT. So it is AC by root 2 divided by 2AC by root 3. Root 3 will come up. AC will get cancelled. So it will be root 3 divided by 2 root 2. Okay, 2. Yes, root 8 is nothing but 2 root 2. So this is the answer. Is there anybody who didn't understand this? Needs more explanation on this? Please pick up. Okay, I hope everybody understood this. And if questions like this comes in the examination, you will be able to do this. Do it. Okay. Sorry, this option should be C. Okay, by mistake, I have written A here. This should be C. Okay. Okay, so let me just take some 10-15 minutes in discussing about this topic, crystal diffraction and reciprocal lattice, because some of you may be MSc first years and I cannot directly jump to the questions. Okay. So these are just the summary slides of this. Okay, you'll be able to understand. Crystal diffraction and reciprocal lattice, wavelengths of X-rays, which are of the order of like angstrom or picometer, and spacing between the layers of these atoms in a crystal is in the order of angstrom. Okay. So what I'm trying to say is the order of the wavelength of X-rays. If this is an X-ray, the order of the wavelength and the spacing between the layers of these atoms. That means if these are the crystals, this spacing I'm talking about, they are of the same order. When they are of the same order, what can happen is, hence, ordered arrangement of atoms must act as a 3D grating to observe diffraction phenomena. In your class 12, whenever you studied diffraction, we used to write one thing, right? That the order of the slit, when you are studying diffraction, the order of this slit should be of the same order as that of the wavelength. Okay. If this is not happening, what will happen? Is it that diffraction will not happen? Can you answer this question? Let me just test your basics. Suppose I have a slit like this, okay, and my wavelength is like this. Will diffraction happen or not?
No,
Why?
because the wavelength is the gap between the slit is more than the wavelength. So
You are just reversing my statement. I am saying that both the orders will be same. And then I'm asking if this is not same, what will happen? You will say no, because they are not the same. You are just reframing the question and providing it as an answer.
we
Anybody
get a
else?
spot.
We get a spot. See, this is a screen. This is a screen. Diffraction won't happen at the edges or whatever it is. Basics. How does this wavelength know whether this slit is big or less?
So the pattern will not be visible.
Yes, you can say that the pattern is not visible. Does that mean diffraction is not happening? What is diffraction? Diffraction is bending of light or something of those sort, right? Yes, you are right. When you say that the diffraction pattern or something will be not visible, it's not that it will not happen, but it's not going to be prominent. See, why are we doing diffraction interference? Because we want to calculate some quantities like the wavelength of light that is coming. Because once we have the wavelength of a source, we know many things about the source, right? What kind of atomic arrangement that source has and so on. Okay. So if the pattern itself is not very prominent, it is useless to us. See, the sun is also, the image of the sun is also passing through the atmosphere. Stars are also, that of the stars is also passing through the atmosphere. Why does stars twinkle and sun does not? Sandeep? It is related. Basic physics.
Sir, because sir, stars are very small in size when
Yes, yes. So that means the sun also twinkles. Okay. But since the size is big, so if this becomes something like this, we will not even notice. But if this becomes something like this, it is very much apparent. Okay. It is like taking, if you steal, if you take away like 10 lakhs rupees from Ambani, he may not even realize. Okay. But if you take 10 lakhs rupees from me, I may cry. Are you getting? So it's like this. Similarly, here, if this slit is big, here also something will be visible, but compared to this bright spot, this won't be prominent. Okay. So that is the reason why we keep the order of the slit and the order of the wavelength to be relatively similar. Okay. So hence, in other words, what we are trying to conclude is, since atomic arrangement are of the order of angstrom, this is something which we cannot change. This is there. You cannot ask God to reframe the entire universe. Okay, it is there. So we have to select something. See, but there is an option in this. We can take micro, gamma, X-rays, visible, everything. But we are selecting X-rays for diffraction. Why? Because X-rays are of the same order. The wavelength of the X-rays are of the same order as compared to the lattice. You have to reverse the thing and try to understand if something is, somebody is using X-ray for diffraction, why? This is the answer. Okay. Sometimes you have these kind of question in your assertion and reasoning. Okay. So hence ordered arrangement of solids must act as a 3D grating. Grating means like it is acting like a slit for this X-rays. Okay. Let's go ahead. Bragg presented a suitable explanation of X-ray diffraction by crystal. It was Bragg who could explain how these things are happening. This figure you must all be aware of. This is called Bragg's diffraction. So let's say these are two planes of the lattice. That means atoms are like this. Okay. And you are allowing X-rays to come and get reflected. So Bragg has proposed a law. You can try deriving this as well, which says that if you're getting a bright spot for a particular angle, this is the angle theta. Theta is the angle between the incident light and the plane. Okay, this is the angle theta. Then for that angle where you're getting a bright spot, this law will prevail, which is 2d sine of theta is equal to n lambda, where n is a integer. Okay. And lambda is the wavelength of this X-ray, and d is the interplanar spacing. This is d. This is your d. So let's say by your experiment, see, you will have a detector. You will have a photo detector here, and this will, you can keep moving this photo detector here and there. Okay. And you can keep moving and see for which point you are getting the maximum intensity of light. Okay, that is a bright spot. Okay, now you fix this. So what is fixed? Your theta is fixed. Lambda, you know what is lambda. Okay, n is an integer, 1, 2, 3, and so on. So based on this, you can find your d. Are you able to see why are we using Bragg's law? Because when you have a crystal, you cannot look through your naked eyes and tell what is the lattice spacing. You have to use X-rays to tell us that. Okay, and for that we keep on using this Bragg's law of diffraction, which is 2d sine theta is equal to n lambda. Are you able to understand this? Okay, so X-ray diffraction is equivalent to reflection by sets of parallel lattice planes in a crystal. But in a crystal, there exist many sets of parallel planes. In what sense? I'll tell you. Many sets of parallel planes means if this is a crystal, one set of plane is this, the other set of planes can be this, and so on. With different orientations and interplanar spacing that can diffract given beam of X-rays. So this will be a different spacing. This will be a different spacing. That's what it is talking about here. The visualization of all these planes is very difficult. To overcome this, the concept of reciprocal lattice was introduced by P.P. Ewald. The regularity of a crystal lattice introduces redundancy when viewed in real space. A crystal lattice is regular, right? It is having some uniformity and some repetition, some periodic variation. So this is called regularity. And it is redundant when viewed in the real space, because each unit cell contains the same information. Because each unit cell contains the same information, is redundant. We don't need the entire crystal. So an analogy of this is the following. A periodic structure is most naturally described by its Fourier transform. Fourier transform means taking it from a position space to a momentum space. That's a Fourier transform. Okay. So example, if you have a function which is a sine wave in time domain, fx equal to sine omega t, the essential information about this function is captured by its frequency. Okay, because if I say fx equal to sine omega t, that means this sine wave is present everywhere in space. It's present everywhere in space. Okay, so space wise it is not very clear. So instead what we use, the parameter we use is the frequency. What is the frequency of this wave? If you're not understanding this, remember your quantum mechanics course. Did you do a free particle? Did you study a free particle in quantum mechanics? When you studied something like a particle in a box, okay, what you did was you did something like this. Something like root 2 by L sine kx. Okay, all these x things were coming. That means you are dealing the problem in position space. But in case of free particle, you have done a Fourier transform, taken things to the k space. Why? Because it's a free particle. There is no concept of any variance in the position. It is uniform all over. Okay. In such cases, what is more important is the k vector. Okay, the wave number we say. Okay, so this is a trick we generally use whenever something is redundant in the space domain, we take it to the frequency domain. For example, one more example I'll give. Let's say this is a wave in the x axis. This is a wave. What we do, we take a Fourier transform and take it to the frequency space. In frequency space, this will be just one line for that particular frequency omega. Okay, so these kind of things we do so that our study becomes more convenient. Okay, so whenever, if this is a voice signal, suppose somebody is saying a note, somebody is saying a particular note, and this is the voice signal for this. A better way of representing this is this, by doing a Fourier transform, so that this is one particular frequency. By that frequency, we can say that, let's say this is a particular note, let's say sa. Are you getting? So coming back, these kind of things are also done in lattice study. Okay, since your normal lattice becomes redundant, we take it to the Fourier space and call this a reciprocal lattice. Okay, so that things become more definite. Okay, please keep, this is just the background why we are doing reciprocal lattice. So similarly, the reciprocal lattice represents the Fourier transform of the lattice in the space domain. The direct lattice or real lattice is a periodic function in physical space, such as a crystal system, usually a Bravais lattice. The reciprocal lattice exists in the mathematical space of special frequencies known as reciprocal space or K space, where K refers to the wave vector. So this is an image I've taken from Wikipedia. This is a lattice. It has different planes. And this is the reciprocal lattice. And this reciprocal lattice vectors will give you information about the spacing of this lattice. Okay. Two lattices are associated with every crystal. These are the direct real lattice and the reciprocal lattice. Using the concept of reciprocal lattice, it becomes very easy to find the interplanar spacing. Okay. So how do you construct a reciprocal lattice? Take a point in the direct lattice as the origin. Let's say I take this point as the origin. Okay. From this point, draw normal to every set of planes in the direct lattice. Let's say this is a particular plane in the direct lattice. I draw a normal. Draw a normal like this. Then this is another plane in the real lattice. This is another plane in the real lattice. I draw another normal like this. Okay, and so on. Then what you have to do, set the length of each normal equal to reciprocal of the interplanar spacing D. That means I have taken this normal. Okay, but how, up to which point I have to go? How did I put a dot here? That is given by, this was the plane, right? This was the plane. So I have to calculate this distance, the distance between two actual atoms. Let's say this is x. Then I have to calculate 1 by x. And this I have to make of a length of 1 by x. Are you able to see why it is called reciprocal lattice? Because its length from this origin is equal to the reciprocal of the actual length in case of the distance between the atoms. Okay. So set the length of each normal equal to reciprocal of interplanar spacing D for its particular set of parallel planes. Place a point at the end of each normal. The collection of points so obtained is called the reciprocal lattice. Okay, that means if I give you a lattice, okay, I just choose any origin. Okay, this is a set of planes. Okay, what I'll do, I'll draw a normal like this. Now, what will be the length of this normal? If this is 2, this will be 0.5. 1 by 2 is 0.5. This will be a point in the reciprocal lattice and so on. If this is another set of planes, let's say this is 2 root 2, then I have to draw a normal like this and I have to go up to a distance which is equal to 1 by 2 root 2. This is how you draw a reciprocal lattice. Are you able to follow? Yes, no? I'm just summarizing.
Sir, I
Yes.
have one doubt, confusion.
Yes, Sandeep,
Uh,
tell me.
You said that the reciprocal of interplanar, the x you let the distance between the interplanar spacing, but x is not the interplanar spacing.
Interplanar. See, okay, I got it. This is plane X. This is your distance X, and 1 by X is this. Okay, I got it. I'm sorry about this. If this is my plane, there'll be parallel planes like this, right? Sorry, not this.
Yes.
Thank you for this. So there'll be parallel planes of this sort. I'm just drawing one plane because this normal will cut all the parallel planes at 90 degree, right? This is normal to plane. So this distance, interplanar spacing. Okay, I'm sorry about this. This is the distance, interplanar spacing, and 1 by x will be the length of this. Is this fine now?
Yes, sir.
Okay, thank you. So now the reciprocal lattice vectors, how do you do this mathematically? If the primitive translation vectors a1, a2, a3 represent a direct lattice, the reciprocal lattice vectors b1, b2, b3 are defined as simple as this. Whenever it is b1, you just take a cross product of the other two, a2 cross a3. Whenever it is b2, you take the cross product, but remember the cycle. It is 1, 2, 3 in a cycle. Okay, it is not 1, 1, 3. It is 3 cross 1, because cross product, it matters whether it is 1 cross 3 or 3 cross 1. Okay, you have to follow the cyclic order: 1, 2, 3, 2, 3, 1, 3, 2, 3, 1, 2, and so on. Okay. Can you tell me what is this quantity? What is the physical significance of this quantity? A1 dot A2 cross A3?
Volume.
Volume
Volume,
of
yes.
the
Yes, the denominator of all this is a scalar which gives the volume of the primitive cell. Volume of what cell? The primitive cell. That means the cell in the real space. If a primitive lattice vector is mutually orthogonal to the other two, its reciprocal lattice vector will point in the same direction. What do you mean by this? If all the vectors are mutually orthogonal, any example of mutually orthogonal vectors? Yes, we have I cap, j cap, k cap. These are mutually orthogonal, right? So what it is saying is, if this is j cap, this is k cap, what will be j cap cross k cap? It will be I cap. Okay, so what it is saying is, if they are mutually orthogonal, then the reciprocal lattice vector will point in the same direction. Reciprocal lattice will point in the same direction, but has a magnitude of 2 pi by mod a. Why 2 pi by mod a? Because this will have a square in this, and this will have a cube. So it will 1 by a will be left out. This is 2 pi. So it will be something like 2 pi by a, where a is the modulus of the a vector. into the same direction. That means for I cap, you will have 2 pi by a I cap. A I cap will have 2 pi by a I cap. Okay. Example in case of orthorhombic lattice, reciprocal vectors are this. In case of orthorhombic, reciprocal vectors are 2 pi by a x cap, 2 pi by b y cap, 2 pi by c z cap. Why in orthorhombic this is possible? Because in orthorhombic we know that alpha is equal to beta is equal to gamma is equal to 90 degree. That means the three lattice vectors are mutually orthogonal. That is the reason why we can do this. B1, B2, B3 are parallel to A1, A2, A3. Only magnitude wise they are different. Reciprocal lattice of BCC is FCC and vice versa. This you can work it out yourself. But just remember this, BCC reciprocal lattice is FCC and FCC reciprocal lattice is BCC. In many questions, you will be given a BCC lattice and you'll be given some lattice vectors, let's say I cap plus J cap and all these things. You will be asked, how will the reciprocal lattice look like? It will be a BCC lattice with this much edge, FCC lattice with this much edge. Such questions have come. So if you know this fact, you can rule out some options. Let's say you are given a BCC lattice, okay, with some information. You are asked about the reciprocal lattice. Option A is saying it is an FCC lattice with this dimension. Option B is saying BCC lattice with this dimension. Option C is saying it is some other sort of lattice. D is saying it is FCC lattice with these dimensions. So you can directly rule out these two options, saying because you know that BCC reciprocal lattice is FCC. Okay, so if you are in a hurry, if you want to rule out some options and take a chance of 50-50, you can use this information. Okay, this will be helpful. Okay, now having said these things, and I also told that it is another way of finding the interplanar spacing, can we go back to this question and try doing this using the concept of reciprocal lattice. Previously, what we did this formula, right? D divided by, something 1 divided by 4 by 3, something. Okay. But now let's go back to this question and see if we can get the interplanar spacing using help of reciprocal lattice. Can you try doing this? I'm giving you 3-4 minutes. I'll also parallelly do. I'm denoting the reciprocal lattice vector by A1 star. So that will be equal to 2 pi by V, 2 pi by V. V is A1 dot A2 cross A3, that is volume, into A2 vector cross A3 vector. This will be my first reciprocal lattice vector. So you have to calculate what is V. Let you also keep calculating parallelly and see if I'm doing any mistakes. V, I can directly write A00 for this vector. For A2, I can write minus A by 2, A root 3 by 2, 0, A. So this will be equal to A cube root 3 by 2. Then, okay, A cube root 3 by 2, that's it. V, are you getting V is equal to A cube root 3 by 2?
Yes, sir.
Okay, good. What about A2 cross A3? What about A2 cross A3? I cap, J cap, K cap. Then A2 is minus A by 2, A root 3 by 2, and 0, 0, 0, A. That's your A2 cross A3. This will be, this is A2 cross A3. This will be equal to A square root 3 by 2 I cap. Zero, and K will be,
Zero.
J will be, no, what about J? K will be 0, but J, something will be there for J. So J will be this into this 0 plus, it will be plus plus A square by 2. Is this right? Mosam,
Yes, sir.
am I right?
Yes, sir. Yes.
Okay. Okay. So my A1 vector will be A1 vector, sorry, the reciprocal lattice vector A1 star will be equal to 2 pi divided by A cube root 3 by 2, A cube root 3 by 2 into A square by 2 will be common. This will be root 3 I cap plus j cap. Is that right? Is this the reciprocal lattice vector? Please check whether this is right or wrong.
Yes, sir.
Can 2 or 3 of you at least confirm that I have done this right? 2
Yes, sir.
cancel.
Yes.
Okay. A square and A cube will cancel. What else is there? Okay. So this will be 2 pi by root 3, 2 pi by root 3. Then this will be root 3 I cap plus j cap. Okay. Now, can you calculate
Divided by
A2 star? Divided by A? Yes. Okay. This one. This is my A1 star. Can you calculate A2 star and A3 star like this? Or will you calculate A2 star and A3 star? Sandeep, what will you do? You will calculate?
I am calculating, sir.
No need to calculate.
Uh,
These are the things you should avoid. Your mind will always tell you to calculate, but you don't need to. Okay, please, I'm going to the next slide. I don't have okay. So, okay, I don't have space here. Anyway, okay, why you don't need to calculate A2 star and A3 star and save your time is because this is the Miller indices given. Okay, your reciprocal lattice vector G looks like H1 A1 star plus H A1 star K A2 star plus L A3 star. Since your K and L values are 0, this will automatically become 0. Only thing that is important to you is this. Are you able to say this? Yes, because this is
yes,
given
sir.
1 0 0. So only this quantity is enough. Okay. Okay, so let me take some space from this. Or do I have any space anywhere? Okay, no problem. So what will be your reciprocal lattice vector? It will be H1 into A1 star. What is H1? H1 is A1. So this is not only the A1 star, this is also the G vector. This is also the reciprocal lattice vector because K and L are 0. Are you able to appreciate this point? K, L 0. So A2 star and A3 star are not necessary. Okay. So what will be the magnitude of this? Can you tell me what will be the magnitude of this? The magnitude of this will be 2 pi by root 3a, and this will be 3 plus 3, 3 plus 1 root over, that is 2. So the magnitude of this will be 4 pi divided by root 3a. This is the magnitude of a reciprocal lattice vector. Okay, and it is the interplanar spacing is nothing but 2 pi divided by magnitude of g. That means it is equal to 2 pi divided by 4 pi into root 3a divided by root 3a. So root 3a will go above, it is root 3a, and 2 pi by 4 pi, only 2 will remain, root 3a by 2. This is another way of doing the same problem. You do whichever you find easy. Anybody, any doubt in this? I'm just repeating what I did. Initially, we did this question using the formula for interplanar spacing in real space, where the formula looks like 1 by d square is equal to 1 divided by root over 4 by 3 h square plus k square plus hk divided by a plus l square by c square. These things we did. For that, we had to calculate what is the magnitude of A, B, C, what are the angles, alpha, beta, gamma, and so on. This is another way of bypassing all these things and doing it easily. All you need to do is calculate the reciprocal lattice vector, this one, A1 star. They are deliberately making the question easy for you by doing 1, 0, 0, so that you don't need to calculate everything. Volume is nothing but A1 dot A2 cross A3, where all these are the primitive lattice vectors. Okay, this you can find by solving this determinant. This determinant we got this value. Okay, on top you have A2 cross A3 for A1 star. Okay, 1, 2, 3. Follow the sequence. You got that to be something. That is A1 star. We know that reciprocal lattice vector G is nothing but H into A1 star plus K into A2 star plus L into A3 star. K0, L0, all these things gone. H is 1. So it is the A1 star is also the reciprocal lattice vector. Take the magnitude of this reciprocal lattice vector, do 2 pi by mod G, you will get the answer. Are you able to follow this alternate way of finding the interplanar distance?
Yes, sir.
Okay,
Sir, is
great.
this 2 pi by mod G is independent of the lattice, sir, or it is something dependent of the lattice we are using?
This is independent. That's why we use this reciprocal lattice. Are you getting this?
Yes, sir. Yes, sir.
Because
Thank you, sir.
mod G itself will have the information of the plane which you are talking, because mod G has this information 1, 0, 0. So in other words, in this process, you don't need to remember different formulas. This will automatically take care of things. And that is the main motive behind finding the reciprocal lattice. Things which are difficult to do in real space that you take to the Fourier space and solve easily. Getting?
Yes, sir.
Okay. Fine. Let's try one more problem. X-ray of length lambda is equal to A is reflected from 1, 1, 1 plane of a simple cubic lattice. If the lattice constant is A, the corresponding Bragg angle is. So what you have to do in this, whenever you see Bragg's law and all you need to do is what? 2D
2D sin theta.
sine theta is equal to n lambda. Okay. Bragg angle will take the first value of n, that is n equal to 1. Okay. So what you have to do? What is asked here? Bragg angle. Okay. Sine theta is equal to lambda by 2d. Okay. Is d given? Is d given? D is not given, right? So you have to find d. But for cubic lattice, what is the value of d? For cubic lattice, the value of d is
Square root
a
of-
divided by h square plus k square plus l square. HKL value is 111. So this will be a by root 3. Okay. So hence your sine theta will be equal to lambda divided by 2a by root 3. Lambda is equal to a.
Pi by 3.
Yes.
Answer is pi by 3.
Okay. Answer is pi by 3. We'll see. So this is nothing but root 3 by 2. So that means root 3 by 2 means sine pi by 3. Sine 60 degrees. So theta is equal to pi by 3. Good. Okay. Are you able to follow this? See, net is sometimes asking simple questions like this. Only you need to figure out things. Okay. Okay. Let's try one more. Probably this will be the last question of the day. This you try by yourself. GATE 2016. Just 1 minute I'm giving you. Then I have to start answering. Okay. Atoms which can be assumed to be hard spheres. Hard spheres, why? Means they cannot be compressed. Of radius r are arranged in a FCC lattice. You should know how an FCC lattice look like. Whenever you draw FCC lattice, please remember, don't start drawing like this and then put something in between. No, this will become smaller. The first constraint in FCC lattice is you have to draw this one, the diagonal of the face. Similarly, whenever you draw a BCC lattice, first adjust this one, the body diagonal, the 3 atoms in the body diagonal. Okay, then do the calculation. So similarly, it is an FCC. So we have to do this. And then the others will come accordingly. Then you are done. This is how an FCC lattice look like, face-centered cubic lattice. Take the center as one of the atoms as the origin. I take this as the origin. Okay, so this will be my what to say. Let's say this is my x-axis, this is y-axis, and something. Take the center as one of the atom as the origin. Another atom of radius small r assumed to be hard sphere. That means this also cannot get squeezed. Why they are continuously using the word hard means so that this cannot get squeezed. Okay, its shape and size will remain the same. It is to be accommodated at a position 0, a comma 2 comma 0. That means this side 0, z also 0, this one a comma 2. That means it will be getting here. Okay, the maximum value of this small r divided by this capital R is. So all you need to do is find the radius of this small sphere. How to do this? It's very simple. See, in FCC, this is the main thing you start with, right? How many radius are there? How many capitals are there from this to this? This to this is your lattice, which is A. Sorry, not no, this is not A. This is A root 2, right? If this is your lattice A, then this is the diagonal. This is A root 2. How many capital R are there in this A root 2?
4.
4
R. Okay, so I'm repeating. This is the lattice constant A.
Hello.
Okay, and this is A root 2. A root 2 is a diagonal. In the diagonal, how many radius are there? 1, 2, 3, and 4. 4 radius are there. Okay, this is one information we have. Now we need to find this radius. This radius is nothing but the total, which is A, minus this is 1r, this is 1r, minus twice of r, capital R. Total is A and minus 2r. What you will get the diameter of this? To get the radius, you will have to divide by 2. So this is nothing but your small r, isn't it? Now A is what? If this is A root 2 is 4r, A will be 2 root 2r, isn't it? A is equal to 2 root 2r. So 2 root 2r minus 2r divided by 2. All the 2's will get cancelled. So this is root 2r means 1.4r, 1.41r minus r. So this is equal to 0.41r. So your small r by capital R is 0.41. That is the answer. Are you able to see? Was it tough?
No.
Okay. And Sandeep, your guessing business is not going to work here. Okay. This is a
Yes.
open answer. Is everybody able to follow this?
Yes, sir.
Yes, no, say something.
Yes, sir.
Okay, fine. So just let me quickly browse through some of the things that I've made. Is something called Wigner-Seitz cell. Okay, I'll be ending today's session with this. Why I've specifically chosen this is not explicitly mentioned in the syllabus. Okay, in the syllabus that I've shown you yesterday, this is not specifically mentioned, but what I'm trying to convey through this is directly related to this thing, to this lattice and all this reciprocal lattice, everything. This is something related. The syllabus cannot mention every small thing. Okay, this comes under the big domain of lattice, Wigner-Seitz cell. Okay, so every small details won't be given in the syllabus. So somewhere you saw this topic in Wigner-Seitz cell. Don't just decide that, okay, this is not in the syllabus, I'll not study. This is a part of the syllabus. That's why previous year questions are important. By looking at them, you know which is coming and which is not. So the motivation, okay, these are some of the things about Wigner-sized cell. I'll just end up by telling how to draw a Wigner-sized cell, okay? Okay, before that, you need to know the definition for the MSc first year people. Where is the definition of this? Yes, Wigner-sized cell about a lattice point. About a lattice point. Note the words. About a lattice point is a region of space that is closer to that point than any other lattice point. That means if I have a lattice like this, okay, I am choosing a region like this so that every point in this region, any point in this region, the closest lattice point is this. If I have a point like this, then for this point, this is the closest lattice point, isn't it? So this will not be a part of this Wigner-sized cell. So in short, you have to draw a structure which we will call as Wigner-sized cell. Any point, take any point inside this. From that point, if you go and stand at that point and ask yourself, which is my nearest lattice point? The answer will be this, which is covered in the Wigner-sized cell. Okay, it is called a primitive cell. It has only one atom in the cell. Okay, Wigner-sized cell is a primitive. It only has one atom because it's obvious from the definition, right? Every point will be closest to that particular lattice point. So definitely the Wigner-sized cell will be having one lattice atoms. Okay, so how you construct? Let's say this is the lattice. You want to construct a Wigner-sized cell for this particular point. Okay, what you do is you connect this point to all the neighboring points. You connect this point to all the neighboring points. Then what you do? You, at the midpoint of every line you draw perpendicular lines. At the midpoint of every line you draw perpendicular lines. At the midpoint of every line you draw perpendicular lines. This, for this, it will be this. For this, it is going to be like this, and so on. Keep on drawing perpendicular lines. That means perpendicular bisector, you can see. You can draw the perpendicular bisector of every connection. The closed structure that will be formed, that is your Wigner-sized cell. In this case, this is your Wigner-sized cell. Okay, you may notice one thing here, that some of the lines are getting redundant. They're of no use. No problem, let them be. Okay, but the closest structure that you will get will be a Wigner-sized cell. Will you be able to construct Wigner-sized cell? The concept is as simple as this. It's a primitive cell covering an area so that every point in that area, for every point in that area, the closest lattice point will be the one inside it, not the one outside it. Okay? Yes, no?
Yes, sir.
Can you draw the Wigner-sized cell for this? So how we'll do this, 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 and so on. Draw the perpendicular bisectors of this. Okay? Then obviously all these things may also come, but their perpendicular bisectors will be redundant. Finally, okay, it's not redundant in this case. Something like this will come, you see? You join all the perpendicular bisectors. And this is your Wigner-sized cell. Okay? In 3D, instead of lines, you have to draw planes. You have to draw planes and you'll get a Wigner-sized cell in 3D. Okay, when you join all these planes. Okay, so this is the last slide. Can we just end up, it's just one. Can we just end up solving this problem? So CSIR net is actually asking about this Wigner-sized cell, but this is really a tricky problem because Wigner-sized cell is for Bravais lattices. Bravais lattice means what? Wherever you go along the Bravais lattice, your environment is identical. I'm giving you a hint to solve this problem. This is the Bravais lattice. Okay, wherever you go, your environment will be identical. You'll see identical environment. You'll feel as if I'm in the same point itself. Okay, but that's why net has very cleverly given this kind of a lattice, which is not a Bravais lattice directly. Can you tell me why this is not a Bravais lattice? You call this as bipartite lattice also. Can somebody say why this is not a Bravais lattice? It is violating one condition of Bravais lattice. Why this is so?
One atom,
Yes.
not one atom per unit.
Number of? No, that is primitive. You are confusing with primitive. Primitive means one atom per unit. But this is This is not primitive, that is fine. But there is one bigger problem in this. See,
So the
suppose you are
distance
here.
between the points varies, sir.
Distance between the points varies.
In a, say, let's say an x-axis, sir. So it's
Yeah.
one small distance
Yes,
for in the
yes. Something like this. Or a better way of telling this is, let's say I consider these 2 points. These 2 points, okay? If you are at these 2 points, your nearest atom is here towards your left. But if I come to this point, okay, in this point, the nearest lattice is towards your right. Are you getting this? So this point is something like this, and this point is something like this. These two are not identical environment. Okay, hence these are two classes of atoms. So what I can do is I can categorize. Wherever there is right, I can call that R, R, R. These points are all R. And wherever the nearest atom is towards the left, I can call this L, 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 and so on. So all these atoms, they are consisting of two types of atoms. Okay, it is RL, RL. Okay, there is no third. Okay, this happens in case of graphene. It's called honeycomb lattice. Okay, so what you have to do is, in this case, if you want to get a Bravais lattice version of this, you have to consider R and L together. You have to consider R and L together. Okay, so I'll consider this. I'll consider this as a unit. That means R and L together as a unit. In that case, I'll get some kind of repetition, you see. Don't you think I'm getting some kind of a repetition? Now, if I go from this branch to this branch, you will find that it is identical environment. Similarly, if I go from this to this, you will find an identical environment. So you have to consider both the atoms together as a unit. It's called bipartite lattice. Okay. So whenever you want to do a Wigner-Seitz cell of this, you have to consider this bar. Okay, both R and L together. Okay. So what will this account to? R and L together. So this is the nearest branch. One branch is this, one branch is this, one branch is this, one branch is this. These are the nearest 4 branches. Then you have to follow the procedure for the Wigner-Seitz cell. One is this, other is this, and this. So your Wigner-Seitz cell will be this. Now they are asking you the area of this Wigner-Seitz cell. Now, by looking at all these vectors, can you tell me which are the vectors that are corresponding to the Wigner-Seitz cell? Is it D1, D2? Is it A1, A2? Is it C1, C2? Is it B1, B2?
B1, B2.
B1, B2, because these vectors are represented by B1 and B2. So what will be the area of this Wigner-Seitz cell? What is the area of a parallelogram whose vectors are given by B1 and B2? What is the area? The area is nothing but B1
B
cross B2.
B2.
This one, isn't it? B1 cross B2. Okay. Now, can you tell me what is the value of B1?
√3.
Huh?
is
Provided this
equal
length
to
is A.
√2.
See, it's very simple. It's very okay. Wait.
A1.
Firstly, we have agreed that this is B1, this is B2, and these are the vectors of a B1 for Wigner-Seitz cell. That you guys have only told me that B1, B2 are the vectors. Now we have to find the area of this parallelogram, which is B1 cross B2 mod. Okay. Now B1 cross B2 mod is nothing but, by the way, B1 and B2 will be equal, right, by symmetry, isn't it? So you can say B1 square into sine of, what is this angle? We'll find out, some theta. Now you tell me, this is a hexagon, right? Everything is A. If this is A, this is A, what is the angle of a hexagon?
120 degree.
120 degree. Okay. So that means this is AA, this is 120 degrees. So this is the opposite diagonal. So this value will be equal to the length of this B1. B1, the length will be equal to A square plus A square minus twice A dot A cos of 120 degree. Can somebody tell me why this is minus? Because the plus will be for this diagonal. For this diagonal, it will be minus. I hope you know vectors. So this will be twice of a square minus twice of a square. Cos 120 means minus cos of 60. Cos of 60 is half. And this minus will make this plus. Okay. So this will be equal to root 3. Yes, somebody was right. Root 3 into a. So this is root 3a. So b1 square is nothing but 3a square. Now, since this is 120, this will be 30, this will be 30. So if this is 30, this will also be 30. Same thing, 30, 30. So 30 and 30, 60 are gone. So what is left? 30, 30, 60 is gone, right? What is left? This whole angle is
60.
120. 120,
60 is left.
60 is gone, 60 is left. So this will be sine 60. Sine 60 degrees. So this will be root 3, sorry. Sine 60 degree means root 3 by 2. So this is going to be 3 root 3 by 2 a square. Let me see if we have an option like this. 3 root 3 by a square. Okay, so that's the answer. 3 root 3 by 2 a square. Okay, are you able to follow this? How to get things like this? Wigner-Seitz cell, how to create Wigner-Seitz cell. But just before declaring something as Wigner-Seitz cell, make sure it is a Bravais lattice. Just like in this case, it was not. We made it a Bravais lattice by considering a pair of atoms. And then we calculate the Wigner-Seitz cell. Is this problem clear?
Yes, sir.
Okay, so I hope I'm able to give you some insights or maybe some different approach of solving some of the problems in condensed matter. Okay, so
one
I
doubt,
have,
sir.
yeah, please tell me.
Sir, what type of Bravais lattice is this bipartite lattice, sir?
No, bipartite lattice means bi means two. This is one just name. I mean, you don't need to worry about this name. That means Bravais lattice means something which is repeating. The lattice points are repeating in a way so that the moment you go to any other lattice point, your environment is same. Okay, but whenever in a lattice point, instead of, see, you know the difference between lattice and basis, right? These are the lattice points as usual, but in the
Yes, sir.
basis are the atoms, right? Instead of fitting one atom, the way you normally do, instead of fitting one atom, you are pairing, you are putting two atoms. That's why you are calling this a bipartite lattice. As
Two
simple as
atoms.
this. Getting? I hope you remember this equation. Lattice plus basis equal to crystal. Lattice points will be one only, but the basis that you are dropping in the lattice points, that is containing a pair of atoms now. Getting?
Yes, sir. Thank you, sir.
Okay. Okay, so I hope I'm able to give you some tricks and tips for this. Okay, I'll meet you tomorrow with one more lecture of mathematical physics. Okay, so I hope you have learned something. Keep revising. I'll send you the lecture soon. Okay, thank you for attending. So I'm closing the session. See you again tomorrow for the last session.